Dear students, so after some 4 lectures of connectedness, it is a continuation in the same series. So we are going to start with connectedness in topology once again. So next topic which we were to cover is components. So first of all, what is a component? What a component is? A component is a maximal connected set. So that means a component cannot be properly contained in another connected set. That means if suppose K is a component, if K is a component and K is properly contained in K dash, then K dash cannot be connected. So what a component is? A component is a maximal connected set. Now we will move on to some theorems related to components. So what is the first theorem? The statement of the first theorem is that every component is a closed set. So what is the statement of the theorem? Statement of the theorem is every component of a topological space is a closed set. So first of all, for the proof, we take suppose X to be a topological space, let it be a topological space, and let K be a component in this topological space X. We have to show that K is closed. We know very well that K is always a subset of K bar. So we know that K is a subset of K bar. Also, we have done in a previous term that if a set is connected, then its closure is also connected. Here, K is a component. So K is a component means K is connected. So K is connected, and since K is connected, by one of the previous theorems we have K bar is also connected. K bar is also connected. Now if K is properly contained in K bar, then it will be a contradiction to our definition of component, because a component cannot be properly contained in a connected set. So if K is properly contained in K bar and K bar is connected, then we will arrive at some contradiction. That means K is not properly contained in K bar. And what it means? It means K is equal to K bar then, because K cannot be properly contained in K bar. And K is equal to K bar directly tells us that K is a closed set. So every component in a topological space is a closed set. Now we move on to the next theorem. So next theorem, the statement of the theorem is in a topological space, every point is contained in some component, and in fact it is contained in a unique component. So I write the statement first. Theorem statement is in a topological space X top, X belonging to X, that means any point, arbitrary point, is contained in one and only one component. So what means one and only one? That means that means x is contained in some component, definitely, for sure, and in only one component, cannot be contained in two components. So first we will show that x is contained in a component, and then we will show that it is contained in a unique component. So let us start with the theorem. So let A is equal to A alpha, where alpha belongs to lambda, be the family of all connected sets containing x. That means in this collection, if the members are suppose A alpha 1, A alpha 2, A alpha 3 and so on, then A alpha 1 contains x, A alpha 2 contains x, A alpha 3 contains x, or in short you can say x belongs to A alpha for every alpha belonging to that particular family lambda. Now, earlier we have proved a theorem that if a family of connected sets is such that their intersection is non-empty, then their union is also a connected set. So here, intersection of all A alpha belonging to lambda is not empty. Why? Because x belongs to each A alpha. So that means x also belongs to intersection. And if x belongs to this intersection, how this intersection can be empty? It is not empty. Each of these A alpha is connected. This is a family of connected sets. So each of the A alpha is connected. Now each of the A alpha is connected and their intersection is non-empty. And we know that if a family of connected sets is such that the intersection of all its members is non-empty, then their union is connected. So what we obtain from here, that union of A alpha belonging to lambda, is a connected set. This is a connected set. Now we will prove that this union A alpha is not only a connected set, but it is also a component. So we claim this union A alpha belonging to lambda, name it that some set you can say K. So we claim that this K is a component. This K is a component. That means it is maximal connected set. That means there cannot be any other connected set containing X which properly contains K. Suppose, if possible, B is any connected set that contains X, then we will show that B is a subset of K. B cannot be a superset of K. So suppose let B be any connected set such that X belongs to B. And what we have to show that now this B cannot be a superset of K, that B must be a subset of K. And that will prove that K is a component. Now B is a connected set such that X belongs to B. But all such sets are members of A. So that means B is also a member of A. B is a member of A and K is the union of all members of K. A. B is a subset of A and K is union of all members of A. That means there will be B also in this union. So that means B is a subset of union of A alpha belonging to lambda, that means K, because B is one among these sets. So B is a subset of K, and that proves that K is a component, because any connected set containing X is a subset of K and is not a superset of K. Secondly, we are to show that this K is unique. There cannot be two components containing X. So suppose it's possible. Suppose if possible, K and K dash are two components such that x belongs to K and x belongs to K dash. Now, x belongs to K and x belongs to K dash. This means x belongs to their intersection. K being a component is a connected set. K dash being a component is also a connected set. Now, K and K dash are two connected sets such that their intersection is non-empty because x is in the intersection. And we know that if there are two connected sets and their intersection is non-empty, then their union must be connected. So this means K union K dash is a connected set. This is a connected set. And you know that K is a subset of K union K dash. K is a subset of K union K dash. Now K is a component. K union K dash is a component. And we know that a component cannot be a proper subset of a connected set. So this cannot be a proper subset. What it means? They must be equal. So this means K is equal to K union K dash. And if union of two sets is equal to one of the sets, that means that set contains the other one. So this means K contains K dash. That means K dash is a subset of K. Similarly, I start once again, back to this step, come back to this step again, that K union K dash is a connected set and K dash is also a subset of K union K dash. Once again, K dash is a component and a component cannot be properly contained in a connected set. That means this K dash is not a proper subset of this, so that means K dash must be equal to this. And K dash is equal to this means K dash is containing K. That means K is a subset of K dash. K is a subset of K dash and earlier K dash was a subset of K, which proves that K is equal to K dash. So such a component is unique. If you take two components K and K dash, they come out to be same. So that means each and every point of a topological space is contained in a unique component. So this was our theorem, and now we move on to the next theorem. The next theorem about the components is that I take out the next theorem.